Hi folks, so in the last video we talked about how we can find horizontal asymptotes. In this video I just want to do one more example of doing that and showing you how or when it's even kind of relevant or hard to do. Okay, so in the last video we ended up kind of wrapping up how to do this, and the idea is to figure out what y value is our graph getting closer and closer and closer to as x gets closer and closer to infinity. Again, we compared these two examples, this first one on the left here and the one on the right here, and I'll circle those. So we compared these two, and so what is the difference between these two functions? Notice that f of x here on the left side, f of x is a 0-degree polynomial over a first degree, whereas g of x is actually a first degree over a first degree. Okay. Now, you can see here that the fact that these are going to be different degrees actually has a pretty relevant effect on where the horizontal asymptote occurs. So on the bottom one, on the left one, when you plug in a big number, well, since the numerator doesn't grow at all and the denominator does grow, it's pretty clear that this one is always going to be it's always going to have a horizontal asymptote at y equals 0. Okay, and this is actually going to be true whenever the denominator is higher degree than the numerator. So another example of something like this would be, let's say f of x is equal to, so I'll just say here, denominator is higher degree. I could do something, I'll do something crazy. So like 1,000 x to the fourth over 2x to the fifth. I'll say x squared, and I'll say minus, 4x cubed, and so on. Okay, and that's my rational function. Okay, looks kind of nasty, and it kind of is, but we can still do the same thing to find our horizontal asymptote. If I plug in a big number for f, so I'll say plug in a big number, what happens? Now, the numerator looks like it's pretty big. I mean, its coefficient is 1,000. Remember, when we're talking about big numbers, we're talking about infinitely big with no bound. And so, yeah, 1,000 looks big now, but 1,000 is nothing compared to 1,000, 1,000. Would that be 1 trillion? So, in a sense, the coefficient actually doesn't mean much. And so, what's happening here is you have 1,000 times a big number to the fourth plus a big number squared all over 2 times a big number to the fifth, minus a big number cubed. Okay. And so what's happening here is that, yeah, there are big numbers all over the place, but what are the most important big numbers? The most important big numbers are going to be the ones with the biggest exponents. And so I like to look at the numerator and the denominator kind of separately. And so in the numerator, the most important piece, the most significant piece, is the x to the fourth, the big number to the fourth. In the numerator, it's the x to the fifth. And so what do we say? Well, that means that when x is really, really, really big, this function is essentially 1,000 x to the fourth over 2x to the fifth. What we can do here is, again, now simplify our function. This is equal to, the simplified version is equal to 1,000 over 2x. And of course, as x gets really big, that gets closer to 0. Again, as x gets big, as x grows. And so if the denominator is a higher degree, this line of reasoning will just get you to x equals 0 every time. Y equals 0 every time. So y equals 0 is our horizontal asymptote. Okay, but what if they're the same degree? Well, if they're the same degree, oh, by the way, we could use the same line of reasoning if the numerator is higher degree. Let's talk about this real quick. Excuse me. If numerator is higher degree, then we're going to have the same line of reasoning. The numerator is going to get so much bigger than the denominator. And so that's going to happen, you know, the function is going to grow without bound. And so it wouldn't actually have a horizontal asymptote because it'll just keep growing and growing and growing. Okay, so going back to this part where the numerator, and denominator approach the same, have the same degree. This is the main scenario that we're going to look at today. Excuse me. And let's pretend my example, g of x equals to, 6x to the 7th plus 3x to the 5th minus 4x over, negative 3x to the 7th minus 3,000. Okay. So once again, we take a look at plugging in g of big number. What happens? Well, the most significant pieces, once again, are the terms with the highest degree terms with the highest power of x. And so that's really just going to be approximately equal to 6x to the 7th over negative 3x to the 7th. Okay, so you might be thinking, like, the numerator is bigger, so why doesn't this one go to infinity? Well, the thing is, like, they're both really, really big, but they're on the same... You'll hear this term a lot as you get closer, as you take calculus, but you hear this term order of magnitude. And, honestly, I don't really quite have the same... I don't think I have the tools or the way to explain it to you, but essentially, they're the same level of bigness, quote-unquote. And we can see examples of this, whereas, like, we could say that if you compare 2 to the x versus x squared, this 2 to the x is actually going to be, like, much, much bigger than x squared when x is really, really, really big. Okay. And you can double check this. So, like, when x equals, well, actually, this is already bigger because, like, when I plug in x equals 5, 2 to the 5th is way bigger than 25. But anyway, because they're on the same order of magnitude, we can't just say the numerator is bigger, so it goes to infinity. But when I have it simplified like so, I can, again, eliminate those. And again, I'm not actually doing this to your actual function. I am looking at the simplified version of the function. And so what I can say is, hey, in this function, when x is really, really big, the only things that really matter is 6x to the 7th divided by negative 3x to the 7th, which is 2, negative 2. And so what we say is that y equals negative 2 is our horizontal asymptote. I want to wrap this up with one other way to do this, and this was a little bit more mechanical, so I don't personally like doing it because I don't think it's as fun, but it will still work, is to do this. So I'm going to use g of x as our example here. Yeah. So one way you could do this is to multiply g of x by 1 over x divided by 1 over x. So this is okay to do because you're just multiplying the numerator and denominator by the same thing. So you're multiplying by a big 1, this is okay. If I do this, then g of x is actually equal to this. Sorry. Not just x, x to the 7th. So I'm dividing top and bottom by x to the 7th. What's the point of that? Well, when I do that, I'll get 6 x to the 7th divided by x to the 7th. Just gets rid of it. Plus 3 over x squared minus 4 over x to the 6th. Divided by negative 3 minus 3,000 over x to the 7th. What's the point of this? Well, when you do this now, when you plug in g of big number, this part's really, really clear to see what's happening is that, oh, wait a minute. When I plug in a big number, these terms are getting smaller and smaller because, again, the numerator is staying the same while the denominator grows. And so this is effectively equal to, again, 6 over negative 3, which is negative 2, which gets you to the same conclusion. Okay. Again, not as much fun, in my opinion, as just doing, this click kind of intuitive math rationale, I suppose. But it'll work. Okay, so again, summarizing, when the denominator is a higher degree, your horizontal asymptote is going to be 0 because the numerator is going to grow not nearly as fast as the denominator. If they're the same degree, then they're kind of gaining size at the same relative rate. And so since it's close enough, you're going to compare their leading coefficients, essentially. And if the numerator is higher degree, then this is just going to go off to infinity, so we don't really typically worry about that, but it could happen. Okay, so there usually isn't. Usually, no horizontal asymptote. Okay, I wouldn't say never, because I suppose there could be one, but I think generally, like 99% of the time, there won't be one. All right, so hopefully this helped. And now let's find some horizontal asymptotes so we could finally graph these fun rational functions.